So thus far, we've found expressions for the partial derivative of the cost function c with respect to weight parameters. We started off at the output layer capital L and found an expression for the partial derivative of c with respect to some arbitrary weight incident to some neuron in layer L. We then stepped back to layer L-1 and found an expression to the partial derivative of c with respect to some weight incident to a neuron in layer L-1. Then we did the same thing for layer L-2 and so on. And then examining some pattern between these generic expressions, we managed to find an overall expression for the partial derivative of c with respect to any weight in our network. Now we shift our aim to the bias parameters. Our goal will be to find an overall formula for the partial derivative of c with respect to any arbitrary bias parameter. And we're going to conduct a same type of analysis where we consider a bias parameter for some neuron v in the output layer. So this would be b, v, l. And then we're going to find a generic expression for partial derivative of c with respect to this parameter. Then we're going to do the same for some neuron v in layer L-1, b, v, L-1, and then for L-2 and so on. And then we're going to look to find some sort of pattern. So let's start by considering the partial derivative of c with respect to the bias term of the v neuron in the output layer capital L. So just as last time, we're going to start off by drawing our tree diagram, which is going to aid us in applying the chain rule. We saw earlier that c was a function of the activations in the output layer, and each activation is a function of its weighted input, and each weighted input is potentially a function of the variable we're attempting to differentiate the outermost function with. And then we multiply derivative terms traversing down each branch, and we added them across each and every single one of branch. And this leaves us with this expression is equal to the sum as I goes from 1 to n of the partial derivative of c with respect to the activation at some neuron I in the output layer times the derivative of this activation with respect to the weighted input times the partial derivative of the weighted input with respect to the bias parameter BVL. Now we can break this derivative down further here, and we get that the partial derivative of the weighted input at the output layer with respect to the bias at the VF neuron is equal to, which is equal to the partial derivative of the linear combination which makes up the weighted input. So this would be the weight going from some neuron J to neuron I in the output layer multiplied by the activation in neuron J of the previous layer. And then we add a bias term for the IF neuron. Then distributing the derivative, we get the following sum as J goes from I to N of partial derivative with respect to our bias in neuron V of the following product plus the partial derivative of a bias term at some arbitrary neuron I with respect to the bias term at neuron V. Now we already established that a given network parameter is not dependent on another, so the partial derivative of one parameter with respect to another will just be 0. And on top of that, the bias parameter, which is incident to neuron V in layer L, does not affect any activation output for some arbitrary neuron I in a previous layer. So this entire expression becomes 0. And we're left with the partial derivative of the bias in some neuron I with respect to the bias in neuron V. And following the same line of reasoning, this partial derivative becomes 0 when I is not equal to V as you're differentiating two separate network parameters. And it becomes 1 when I is equal to V because you get the same two infinitesimal quantities in the numerator and the denominator. So we can write this down as 0 when I is not equal to V, and when I is equal to V, we get the following expression, which is just 1. This means that the partial derivative of the weighted input in neuron I is equal to 0 when I is not equal to V, as this term becomes 0, and it's equal to 1 when I is equal to V. And so substituting these terms back into the sum, we see that as any summation index not equal to V yields 0, our summation disappears, as we only get a non-zero term when I is equal to V, in which case this partial derivative becomes 1. So when I is equal to V, we get that partial derivative of C with respect to the activation in neuron V multiplied by the derivative of this activation V with respect to its weighted input multiplied by 1. Now we're done with the output layer L, and we move on to layer L minus 1. So now we're at layer L minus 1, and I'm going to consider the partial derivative of C with respect to some biased term in neuron V in layer L minus 1. And just to streamline the process a bit, I'm going to draw up our chain rule tree diagram, or rather copy paste it here. As usual, the cost function is a function of the output layer activations, which are in turn functions of their respective weighted inputs. And then the leaf nodes become the variable we're trying to differentiate the outmost function by. So following our tree diagram as an aid, we get that the partial derivative of C with respect to BVL minus 1 is equal to the sum as I goes from 1 to n, as we're adding across all the n branches of this tree diagram of the partial derivative of C with respect to an output neuron activation multiplied by the derivative of this activation multiplied by the partial derivative of the weighted input at neuron I with respect to the biased term of neuron V in layer L minus 1. So now we can continue by breaking down this derivative further, in which case we get that the partial derivative of the linear combination which makes up the weighted input. And this would be the sum as j goes from 1 to n, where you multiply the weight going from neuron j to neuron I in layer L multiplied by the activation of the jth neuron in the previous layer, and then you add the bias term for neuron I. And then distributing this derivative, we get the following. If you consider these separately and start with this bias derivative, here we have to ask ourselves, if we consider some neuron I in layer capital L and a bias term for this neuron, how is this bias term affected by the bias term for neuron V in layer L minus 1? And as usual, since they're network parameters, one does not affect the other, which means that this derivative becomes 0. Now, as for the derivative of this product, we also have to ask ourselves, how does this bias term affect weights going to the output layer and activations from layer L minus 1? So once again, if you consider some weight going from some neuron in the output layer, how would such a weight be affected by this bias term? And once again, we'll reuse the same line of arguments, which is that the weights and biases are network parameters, which we set ourselves, and therefore a given weight parameter is not affected by a change in this bias parameter. Now, as for the activations in layer L minus 1, we see that this bias term would not, for instance, affect the activation of neuron N in L minus 1, as this bias term does not affect the weighted input for neuron N. But the bias term will affect the weighted input for neuron V and therefore the activation at neuron V. So if we go back to our derivative, we get that the weight parameter is not affected by a bias term, which means we can take it outside the derivative. And what remains is the partial derivative of the jth neuron in layer L minus 1 with respect to the bias parameter. Now we can further break down this derivative. And as we stated, the only activation in layer L minus 1, because neuron V is the only neuron in which the bias term is incident to. For any other neuron, for instance neuron N, the derivative of the activation with respect to the bias term in neuron V would be 0. So when J is not equal to V, we get a 0 term. And when J is equal to V, we get the activation in neuron V with respect to our bias term. It's the case when J is equal to V, and we get 0 when J is not equal to V. Now we can take this derivative and continue it here. Now once again, recall that an activation is a function of a weighted input, which then may be a function of the variable we're trying to differentiate the outermost function by. So utilizing this tree diagram and applying a chain rule, we get that this partial derivative is equal to the derivative of the activation with respect to the weighted input. Once again, a regular derivative because activations are single variable functions of weighted inputs, multiplied by the partial derivative of the weighted input with respect to our bias term. Now we can unpack this derivative, partial derivative of the weighted input. And if you write out the linear combination which makes up the weighted input, we get that the partial derivative of this weighted input is equal to the sum as k goes from 1 to n of the weight going from neuron k in layer L-2 to neuron V in layer L-1 multiplied by the activation in neuron k from layer L-2. And then we tag along the bias term for neuron V in layer L-1. And distributing this derivative too, we get, and then right off the bat, we see here that we have the same infinitesimal quantities in the numerator and the denominator, so this expression just becomes 1. And as for the derivative of this product, we have to consider if we change the bias value for neuron V in layer L-1, then how will this affect some weight going from some arbitrary neuron K in layer L-2 to neuron V, that is W, K, V. Applying the same argument as we've done up to this point, changes in this bias value would not affect this weight. Then we have to consider the activations in layer L-2. So if we first consider the activation of neuron N in layer L-2 and how changes in this bias value affect this activation. And we're going to use a similar argument which we use for weights. And our argument here will be that this bias term lies ahead of the activations in layer L-2 and therefore do not affect any weighted input in layer L-2 and therefore by extension no activation in layer L-2. So this bias term wouldn't affect, for instance, an arbitrary activation AK L-2. This results in this derivative becoming 0, which means this partial derivative becomes 1 because this term was 1.